Okay. Hello, everybody. I apologise that we are a couple of minutes late. It's because our excellent hosts at Macmillan are having technical issues. So they're going to try and join us. So I have to do the housekeeping and introduce myself. Not really what you're doing. However, I have been asked to say that you will receive a certificate, which is, if you'd like to type woo woo in the chat, that would be great, because I know you're very excited about that. Well, thank you, first of all, for giving up your time. I'm hoping that the good folks at Macmillan will sort out their technical difficulties. Let me introduce myself. Hello, I'm Andrew. There we go. I don't really know what else to say, but it's good that you're here. There's quite a lot of you here. So I will, for the next 40 minutes or so, just try and take you through this thing that we've called thinking and working mathematically. So I'm going to start from the basic assumption that if you do know stuff, that's a bonus, because I'm going to go very quickly through the basics of Max Maths. Now, I guess you know something. You know that it's a primary maths course, and based on the curriculum that Cambridge put out. Now, you'll probably also be aware that the Cambridge International Curriculum changed a year or so ago. And I think, like all publishers, they've been taking a good look at their textbooks and their schemes and wondering if they need to update it, whether it would be helpful or not. That's what this is about. So the second edition of Max Maths hasn't changed hugely. It's changed a little in some kind of small, but I think significant ways. So I'm going to take you through that. Now, I apologize if some of this you already know, but we will get to the what is different stuff in the second half of our session. I'm hoping I can click. I can. Okay, there we go. So I wasn't sure whether I'd have control or whether the good old Macmillan people. Oh, hang on. I'm just going to pause. A couple of people can see, but not hear. Now, can anybody see and hear? I'm just going to wait for some chat. If you can see and hear me. Okay, then my apologies to the person who can see but not hear, but logic tells me then that's probably an issue with the sound at your end if it's coming out this end. So yeah, you might have to check the sound settings on your computer. That's not a very helpful thing to say because I'm obviously miles away, but I hope you can. All right, and I just realized you couldn't hear that, so what a waste of a sentence that was. Sorry. All right, so the features of Max Math, the second edition, and a focus on this thing we're calling thinking and working mathematically, which is a significant new thing. Okay, and we're going to look at just some examples from the textbooks. I've spent quite a long time going through the textbooks, trying to pick out some examples of not only, I think, what Max Math does particularly well, but of the significance, the changes, and how we can draw out this thinking and working mathematically idea. All right, so feel free to put questions and things into the chat. Obviously, they're at the moment, Macmillan may or may not be able to feed them, although they are. I am able to engage in a chat with them. I can see I've got a second chat, so at least that bit's working. So do put some questions in, and maybe they can filter those and feed those for me at the end. I should say, by the way, I am a teacher. I love teaching. And in fact, I've just been teaching this morning. I've just been teaching about area and perimeter. So I live and breathe this. I don't want you to think I'm just someone they've sort of dragged in off the street to talk about these things. And also, I helped with some of the new the version 2 of Max Math. So I'm actually quite a fan of it. And here's one of the reasons why. Okay. The 4 components, these 4 books that I showed you, are terrific. There's a book for the student, which I guess you'd call a textbook, and that is this one. Okay, and it looks like you'd expect a textbook to look. Here's the grade 1 book with obviously plenty of visuals, chapter section headings, and so on. And that's very much for something for the teacher to introduce the students with. They go through the examples. Then there is a workbook. Now, the workbook is more independent work, this, and you can see the kind of thing, very similar to a lot of different things, but they write in it. They put their work in it. The other 2 components are a journal. And this again is a much more independent thing, but there's a lot of what we call metacognition in here. I'll just pick a page at random. What can I do? What do I know? What have I learned? So it encourages students to be very reflective about their learning, which, as we all know, helps them learn. They'll need a lot of guidance when they're younger for this, of course. But now, and finally, arguably the most important component is the teacher guide. Now, the teacher guide has got some very detailed, and these have been quite widely rewritten. They are really good. Now, you may or may not be a specialist maths person, but this talks about every section in the textbooks. It talks about how to introduce it. It gives you activity ideas. It gives you important questions. And I think particularly brilliantly, it picks out key misconceptions. So when you're planning with Maths, you'll go, what might the misconceptions for this topic be? Oh yes, squaring, they think that means multiply by 2 is a very common. So the authors have a lot of experience, and they have picked out the kind of misconceptions that if you've been teaching a while, you'll know come up year after year. Oh, I mix up area with perimeter, that sort of idea. So those are what you get. There is also, and it's beyond the scope of today to talk about this much, but there's also an online component called the Teacher Presentation Kit, which is a very grand sounding thing, but it's very good. It allows you to take pages from the textbooks and display them, and there are interactive videos and elements of it. So it just basically augments the practical physical resources that are already there. Right, so where does it come from? Now, this is super important. This is really important. It's built on the Singapore maths philosophy. You probably know this well, but the Singapore maths was created way back. Singapore's quite young. Singapore's actually about the same age as me, and mathematically, they realized they wanted to start from scratch, clean slate. What is the best practice? And they went all over the world, and the Singapore Education Ministry tasked a gentleman by the name of Dr. Fong, who I've met, and he's an absolutely wonderful man. And he said, I went to Britain. I came and did my PhD in maths education in the UK, and I kind of picked up from the UK these ideas of Zoltan Dinesh and Jerome Bruner, neither of whom were British, of course, but this is where he learned about them. And so the Singapore maths is based on this kind of pentagon. So the metaphor is of building a house. So they said, well, let's get the foundation in first. And what is it? What are the concepts? So basically, you want to build a house, you put the foundations in first, and that is deciding the concepts. So you'll find these are the 6 numerical, algebraic, geometrical, and so on, that they said this is the fundamental essence of a mathematical education. Now, you could maybe argue that there's some kind of logic as well in there, but those are, just, I guess, topics, you would say. Then we put the walls of our house up, and those are the skills on the one hand and the processes on the other hand. And this is where you get the reasoning from. So they're very strong on reasoning. They're very strong on heuristics, bar models. And of course, what skills do you need? Well, you need numerical skills. You need calculation skills. You need to be able to visualize and so on, and analyze and estimate. And so those are the skills. And then the roof of their house are effectively their attitudes. And this word I've already used before, metacognition, i.e., reflect on your learning. How did that go for you? One of the best schools I ever went and visited was in Brunei. I go out to quite a lot of schools to try and help there. And they at the end of the lesson would say to children sometimes, where were you working today? Were you in your comfort zone? Were you in your danger zone? Were you in your challenge zone? And obviously, if you use that too often, they learn that there's just a correct answer. But actually, what I like is it just gives children a chance to reflect. Oh yeah, how was I doing today? How did I tackle that? And confidence. I will just mention perseverance. I don't know where you are around the world and where you work around the world, but since COVID, I've noticed that here in the UK, where I'm based, perseverance has taken a real battering. And I think it's only now really that we're beginning to see that perseverance, or persistence, as we sometimes say, is something that we need to work on. Because that resilience has taken a bashing, as I say. And so I think if you've got if you've got textbooks that lead you through interesting activities, if you've got challenges, if you've got support and scaffolds in place, then it's going to really help you. So those are the 5 core philosophy principles of Singapore Maths. And then the sort of the features, which is kind of connected. The features are that they start from problem solving. One of the reasons that children are put off maths is they don't see the point. Like, why am I learning this? So start with a real problem to solve. We'll come back to that later when we look at some data exercises. There's an emphasis on visualization. You'll all have heard of the bar model, not as it's wrongly called the Singapore bar, but just the bar model. Now, the importance of visualizing things, because if I say visualize a cat, you can. If I say visualize a mug, you can. If I say visualize 7, that's a much more difficult thing to do. You can visualize 7 fingers maybe, or a line and a line, but that doesn't look 7-ish. Any more than if I was to write k, a, t, that doesn't look like a cat. So this idea of visualization is super important. Now, the spiral curriculum, this is not a new idea, but the spiral curriculum is that you revisit ideas constantly, but at a slightly higher level, hence the idea of a spiral or a spring. And this goes back to Dean Zoltán Dínes from Hungary, and it's not new, but it's built in. So every year you revisit multiplication. Every year you revisit addition, but at a higher and higher level. CPA, I'm sure there isn't a person in the webinar who doesn't know about CPA, concrete, pictorial, and abstract visualizations. And then finally, this emphasis on teaching concepts and rather than just creating parrots who can just copy something you do. So real depth of understanding. And I've seen this in practice. I went to Singapore and sat in a classroom and was blown away by that. So might get to that if we have time. If not, you can ask me the questions. All right, so that's what Max Maths has been built on and why. Now, as I said, here comes the Cambridge curriculum, because thinking and working mathematically is what we want to think about today. And so I went into the Cambridge curriculum, and this is what's changed. So they say it's a key part of their curriculum to assist learners to consider the processes involved. If I just go back to the previous slide, can you see this is the process, the emphasis on conceptual understanding? What are the processes? And back here, of course, the processes are absolutely fundamental. One of the 2 walls of our house that we're building. Okay, and so thinking and working mathematically is a bit of a mouthful. So they've broken it down into these 4 areas: specializing and generalizing, conjecturing and convincing, characterizing and classifying, critiquing and improving. And what I didn't realize when I first started doing this is that is a very good summary of what mathematicians do. I think if our curriculum is too much exercise A, well done, now do exercise B, well done, now do exercise C, well done, then children could be forgiven for thinking that maths is about collecting ticks. And it's not. It's about, as John Holt famously said, the true test of our intelligence is not what we know, it's how we behave when we don't know. And I think that's great. But with the loss of resilience, children don't like not to know. And also culturally, there's in a lot of Asian jurisdictions I've traveled around, and I've noticed that there's a sort of perceived sense of shame of saying I don't know. But actually, how can you conjecture and how can you improve unless you're prepared to admit that you don't know? So I think that's a really important and quite subtle, and for some children, slightly uncomfortable change, because they like being fast and correct, and there's nothing wrong with either of those things. But if those are the things we praise above everything else, then their willingness to try things out and take risks will go. So I think this is quite a clever way of breaking it down. Okay. Right. I've just had a message in from Macmillan, apologising again for the technical difficulties. They are trying to get up back on, but if not, please can I wrap it up? And I will mention that the certificate and slides and recording will be available. I think probably I should legally have said this session is being recorded. It is, so if that's a problem, please let us know. All right, and we will remove your name if you so require. But those are, if I forget to say it at the end, that at least I've said it now. Okay, let's move on. So I looked then at the actual text of the Cambridge curriculum, And this one thing jumped out at me when I was thinking about how to define this. In strand 6, okay, statistics, identifying patterns. Now, the hottest ticket in town at the moment is data analysts. I have lost track of the number of people who tell me they're crying out for people who can analyze data. I mean, we know this as well. You know, the extraordinary length to which companies are trying to get our data, and they'll pay for it. They'll give us freebie stuff in exchange for our email address, because they know that the people with the right skills can spot patterns in our data. There was a very famous example in America a few years back when a man wrote a very angry message to a supermarket because they'd been sending his daughter, his young daughter, teenage daughter, emails with special offers for maternity wear and things. And he said, "How dare you? My daughter's not pregnant," you know. And it turned out she was, and they had identified this correctly, even though he hadn't, just from the kind of things she was buying and looking at online. So data, being able to analyze data and spot patterns, is a real massive skill. Okay, so what do I mean by identifying patterns? Well, let me tell you a wonderful story. I was in Rome about 10 to 15 years ago, and I was supporting the teachers in a lovely school there. And in the year 1 class, there was this wonderful carpet with all the numbers up to 100 on. And I rather liked that carpet. I was hoping we could get one in our house, but apparently we're not allowed. Anyway, there was also a box of Numicon shapes on the wall. And I've done lots of work with the amazing people at Numicon over the years. And so when I saw it, I asked the nearest child, "Oh, what are those plastic shapes?" And he said, "They're numbers." I said, "Are they? I thought those were numbers." And pointed to the rug, and he went, "Oh yeah, they're numbers too." I said, "But they look very different. What number's this?" And I picked up the 8, the green piece with 8 holes. He said, "Oh, that's number 8. I said, "Oh, put it on number 8 then. Put it on number." And he laughed and he dropped it on number 8. Anyway, I walked away, and I was in the classroom about another 2 minutes, just talking to the teacher and looking around with the other children. And when I came back, this was what I saw. Quite on their own, what they had done was what I'm going to call specializing and generalizing. You see, 8 is a special case. There it is. That green piece sits on the number 8. But then they thought, "Oh, what? 18's got an 8 in it. Maybe we could put one on there." And his friend went, "Oh, but it needs a 10." And so they put a 10 and an 8 on the 18. And you can see they went down. And after a while, they started to realize that, oh, everything in that column was going to have one green bit and a certain number of blue bits. And of course, what they're learning is place value. They don't know that, and they're not using that phrase, but they're seeing the structure. They've identified the pattern. And you can just see they've started to realize that something very similar is going to happen in the 7 column, where there's going to be a pink one. And if you think about that photograph, that is one of the most powerful things I've ever seen. The corollary to that story, which is absolutely gorgeous, is this. The teacher said, "Oh, that's incredible." I said, "Can I take a picture?" She said, "Yes." "But that's not why it's incredible." I said, "Why is it incredible?" She said, "Because that particular child," and the angle of the photo means you can't identify them, so I was allowed to use the photo. "That particular child has never spent more than a minute on anything before. They've never focused on anything maths before. And suddenly here they are sat at that carpet, completely focused on this task." So I think there's something rather beautiful about that. I think there's something rather nice about children liking pattern. We're naturally attracted to people with symmetrical faces, for example. Why would that be? We're naturally inclined to see pattern and structure. And I think that sends a great message to children. If we focus more on maths being about pattern and structure than about do exercise A and long multiplication and put a decimal point here, then I think they'll enjoy it more. And with enjoyment, you'll get engagement. Okay. So now let's go to an example in the Max Math book, which is kind of related to that, really, the idea that there's a connection between 8 and 18 and 28. So here's an example. Now, this is from year 6. We've gone all the way up the grades. Now, here we go. So this is another example of specializing and generalizing, but how it might look. So let's have a look. Here's a question. Tia starts with this number, 1.4 million odd, and counts by 10,000s. Okay, And there's an example of how it works. You can see the jumps of 10,000, kind of number line jumps. But I like the question box. What digit changes when I count by 10,000? And it's going to be the fifth digit from the right, obviously, because you've got, so I shouldn't say obviously, that's a really bad word. Ones, tens, hundreds, thousands, 10,000. So that digit goes up by one. And then, of course, what number comes next? So that's a general rule. Okay, but also a specific answer. Now, I think it's very easy to incorporate some greater depth into this by saying what number would have come before the starting number. And then she's got to realize that there's an inverse concept here. So it would be 1, 4, 3, 5, 206, and so on. And what doesn't change? I think one of the great mathematical questions is what changes and what doesn't change. You know, what do you notice here? What stays the same? What's the pattern? If I just quickly go back here, look at this column. What changes? The number of tens. What stays the same? The fact that it always ends in an 8, and so on. Okay. If I was to look along a row, for example, let's look along the row that's that 26 in it. What changes? The piece that isn't blue. What doesn't change? The number of blue pieces is going to be 2 in every section. So there's a really great, powerful questions to ask to upskill your students. Okay. Now, as you would expect, there is some spiraling here. So we could also count on back in fractions. Now, this suddenly, from what might seem like quite a simple question, we've got a much more deep one. Can you see this? Just have a look at that question. And you can see that that is requiring children to do the same thing, but at a slightly deeper level. And this time they're given the numbers. This is variation theory. They're given the numbers, but now they have to work out the size of the step, which is quite easy in the first one, not so easy in the second one, a little easier in the third one, and depending on how you spot it, and the fourth one not too bad. So there's the the numerator. So we're going down by 3/5 and so on. So notice how we're counting on and back, and that's very good that varies. It's really important. All right. Now, another example. This now is about a general rule, because generalizing is an algebraic idea as much as anything. Can you say what goes on? So, for example, I really like this question. Here we go. This sequence shows the first few numbers in the 4 times table. Well, I can ask you what the next one was and the one after that. But if I asked you the 50th one, well, I don't know. Oh, okay. It's the term 50. So it'd be 50 times 4, because I've noticed that the first term is 4. 1 times 4, then it's 2 times 4, and so on. Okay, so this is a general rule. And this idea of general rule, or it's sometimes referred to as the nth term, is a very powerful one because we can predict what's going to happen. I'll tell you a fun game, actually, you can play. You might not have these books, but here's a fun game you can play that starts to get children thinking about it. First of all, ask them to write down their name. And they can use capital letters. So let's say I'll take my name. So my name is Andrew, and I would write Andrew. But then next to that, they write it again as though it was a long word. So I'd write Andrew. And then you ask them, what will be the 100th letter you write down if you kept writing that? And so they have to really think. Now, if they're lucky and their name's got 5 letters in, they can probably quite quickly work out that, okay, let's say I'm trying to think of someone, Jenny. Let's say my name is Jenny, Jenny, Jenny. Yeah, okay. I'm pretty sure that every 5th letter will be a Y. Okay, but I could make that harder. I could say, okay, what will be the 38th letter? And it's quite fun. Just see how you get on with that. It's a quick little starter, but it allows children to think about specializing and generalizing because they are, as we said before, spotting patterns. Okay. Next slide. Here we are. Now let's go back into Key Stage 1, or sorry, Grade 2, Year 2, to look at the second aspect of working and thinking mathematically, and that is conjecturing and convincing. Or in less posh language, I think this, and here's why. This is what I think, and here's why. But conjecturing and convincing sounds a lot more grown out, doesn't it? Okay, so let's have a look at this. Samir puts an equal number of red and yellow counters in a bag. He takes one out. He makes a note of the color on a tally chart and he puts it back. He does it 20 times, and here's his data. So we can have a look at the data. He's got 11 reds, and you can point out the 5 bunches of 5s there, and he's got 9 yellows. But this question, why do you think the frequency values are close together? Why do you think? And that's literally conjecturing. Okay, so even though the word conjecturing may not appear necessarily in the book or in the teacher's guide, you can say, okay, come up with a theory. What do you think? Why? Have a chat with someone. Do you think somebody will always get the same results? A lot of children will say yes, and I think that's it. So can you convince? It's almost more important that you're able to defend your answer than that you have one. It's almost more important that you can justify your position, kind of like in a marking essays when they get a bit older. Yeah, the person marking their essay isn't so interested in what their view is, it's how well they argue their view. And I think that's a really important thing. So let's have a look at another example of conjecturing and convincing. This time a little bit older. This is year 4. And I had to read this a few times. So the Max Math teams played a computer game. They recorded their scores in a bar graph, and all the scores were quite high. So they had the number scale go up by 10 each step. And that's quite a step up for year 4, because up until now, they've been able to read the scales exactly. But now it might be approximate. Now, I think they've been quite kind on this particular one, and they've made sure that all the scales go up to, I think, an exact multiple of 10. Right? But they might not have done. So that's a new thing to introduce. So good to see the axes are labeled, the players, the scores, okay, and the title. All right. But look at this question. I just love the question. What can you say about the scores by looking at the graph? And you could say very basic things like, well, Han could say, I got 60, and Jade could say, I got 50, and Toby could say, I got 40, and Padma could say, I got 50, but none of them say that, do they? And I like that. I got the same. How do you know? It's the height. I got the highest. How do you know? Well, that's interesting because the word highest has 2 meanings, both of which fit here. So it literally is the highest bar, but also the highest score. I got the lowest. Ditto. I scored 10 less. So did Han score 10 more? So I think, what else can you say? Which 2 players scored 100 points between? What was the average score? There's so many different average, probably not in year 4, but there's so many different things that you can do. You can conjecture. You can say, what could I think? What could I try? And if we want, who's unlikely to win if we play 100 times? That kind of thing. So you can really open it up. It's not just about what is the answer to this sum. All right, let's have a look at another example. Now this one in year 6, I picked this because it's similar to, it ties back to that idea of sequences, but again, there's the pattern. They're always asking us for pattern. I would say in primary maths, the most important thing that children will ever learn to do is to look for a pattern and to use the pattern to predict. And that's really important, what will come next, because that's what makes us such good problem solvers, I think, is that we can predict, we can plan ahead. So look at the sequence of dots, and Tia notices that they form squares, and you'd be amazed. You would literally be amazed how many children don't know why square numbers are called square numbers, and it is because you can put them into a square. Okay, and that's literally it. Okay, so yes, they'll tell you it's 3 times 3, but they won't know why it's called a square. So that's why we put into the textbooks this idea, because of the shape they make, the numbers in the sequence are called square numbers. And here we go. Conjecture again. What do you think the next 2 square numbers are? Now, it's not a difficult question, particularly if they spot the pattern. In fact, it's a very easy question if they spot the pattern. But the point is, we are conditioning them to look for patterns and make predictions. And of course, there's another interesting thing, which is the number of extra dots. And you may never have known this yourself. The number of extra dots goes up in odd numbers. So, for example, to get from step 1 to step 2, you add 3. To get from step 2 to step 3, you add 5. Then you add 7. Then you add 9. So for reasons which are beautiful, but we won't go into now, square numbers go up by successive odd numbers. And I think that's a real lovely moment for some children. Okay, so now let's have a look at the third of our 4 aspects of what we think thinking and working mathematically means, and that is characterizing and classifying. So this is a very mathematical idea, isn't it? Sorting things into groups. So even back in year 2, we're distinguishing here between tens and ones. I've got 4 of this thing and 2 of that. One thing I've been really keen on trying to think about with children more in the last few years, and in fact it's been written into the teacher guides for some of these ideas, is the idea that numbers can appear to be like adjectives. They are literally classifying. So for example, in that first example, 42, the 4 is an adjective in that it's describing our tens, and the 2 is an adjective in that it's describing how many ones we have as well. And for children who struggle with place value, this can be quite a game changer. So you can see this, and there's a game, think about a number. So they're starting to, even really with early place value, they are classifying things. So I'm trying to think of a good example. Yes, in the second one, the purple one, 5 tens and 6 ones. Extremely interesting, I think, is the fact that the 5 is worth more than the 6. Because although 5 itself isn't worth more than 6, 5 tens is worth more than 6 ones. So that's why it's important. 5 of those things and 6 of those things. Yeah. So it's more obvious if it had been something like 5 years and 6 days. 5 years and 6 days. That's that's good. Yeah. Okay, now I can clearly see that the 5 years is worth more, and it's the same as 5 tens and 6 ones. So classifying, characterizing, very useful. Let's move on. Here's one from year 4, book 4. And again, the classic Carroll diagram. Complete this diagram by drawing and naming a 2D shape. Now, this is arguably more difficult because it doesn't give you the shapes to start with. So you have to find a shape that will fit. So that's characterizing. Can I characterize a shape and then classify them? Okay. Same in the second one, but for 3D shapes. And then on the right-hand page, you've got this idea of what you'll see in Max Maths is heads together. And this is the chance to really go for that kind of wondering and that problem solving together in teams. Okay, so grouping things together. So again, characterizing, classifying, data sorting, and so on. In year 5, here's a simple, obvious example of angles. Now, this idea we came up with for lolly sticks. Put this in because in grades 3, 4, 5, we sort of lose the fact that an angle is about a turn. All right, it's not a fixed thing, and an angle is not a point. Okay, when you see a point, there has been an angle turned, or what that would need to turn from this to here. Okay, so by using lolly sticks and pins and things, we can show them. But again, we need to classify angles, and in those boxes on the right, it just gives you the classifications of angles. Although problem solving is important, Max Math doesn't, and nor should it, shy away from just giving students information. You're not going to guess it's called acute angle or a right angle or a reflex. You're not going to guess those things. So those are things that you just need to be shown. And the protractor as well, how to use one of those. All right. So classifying, characterizing, giving them the names. All right. And then let's move to another example. Here we go. Look, it's not the most exciting, but it's a very useful page, and it's a review. This is basically a review. What have you learned about 2D shapes? What have you learned about 3D shapes? And classification is all about features. So what are the features? So we need that language again. Okay, so what are the features? Well, we talk about sides, we talk about vertices, we talk about edges and so on. We talk about faces. So all of that language has to come in. So language is a very, very big part of characterizing. Okay, let's move on. Don't want to overdo the time. So I like this into grade 6. Now this is one very significant new section, I think. So as a class or in small groups, choose something you'd like to find out about. Now let's just stop for a second right there. Often, how often when we teach like data handling stuff, do we just teach them, oh, this graph shows this or this one shows that, but we never start from why does it show that? Why do I care? So this turns it on its head. You should always want to know something and then learn about how to do the the data. So this very much turns it on its head. So here's the heads together. What do you want to know about? Now that's a big question. So it's scaffolded for it. So there are some 4 examples. There's 3 examples here. You might want to find out how busy a road is. Yeah. What if you could go to your local government representatives and say, we've done a survey of cars and you can see between these times there's this much traffic and we think it would be sensible to put a crossing in. Yeah. So it's about convincing, it's about presenting data and so on. Or what people's favorite sandwiches. Why do I care? Well, I might care if I'm buying a lot of sandwich fillings as a school and I want to make sure that they don't get thrown away. I want to make sure that everyone actually likes them. Yeah. So waste less. Or perhaps I'm designing a new cap. I need to find out what size your head is. Yeah. So I've kind of given children there. We have 3 examples of how that might be, helpful. Okay. And then you can take it on to, okay, now when you've finished collecting that data, look and you've drawn your chart, what does it help you find out? Does it show the results? And that's metacognition. That's really reflective stuff. So, but critiquing. Now, critiquing. What could you ask other people to see if they understand? You see, not all graphs are very easily understandable, really. We know that, okay? So find questions that you could ask people, a survey. And how could you use your data? That's a question I almost never see asked. How could we use our data? So if anyone does ask that question, it's jolly good, okay? That's critiquing, that's improving. Yeah, it's saying we can always do better. Now, those are the kind of 4 aspects I think that are really interesting for me. Now, I'm going to talk fairly briefly and then open it up for questions about embedding CPA. The CPA, we start with something physical, okay, and then we add, okay, a picture, and then we show something abstract. Now, this is great. So here's two footballs. I can write it in letters. I can write it in this funny shape, or I can write it as an abstract idea, this dots. Okay. And there's a lot going on here. All of these things mean 3. All of these things mean 4. So it's very subtle. And this is how book 1 starts. Okay. It's really nice. So what it doesn't mean is you move away from concrete when you get to pictorial, and you move away from pictorial when you get to abstract. That is not what it meant. Okay, so Bruner's theory was more about adding, more like ripples in a pool than a single linear journey. Again, probably the time for another webinar. Okay, look at this CPA and place value. Notice how I'm sure you've all used counters to represent digits, and this really ties back very nicely to what we were saying earlier about adjectives. So in Max Maths in book 3, we're looking at, I've got 4 of these pink counters. And each of those pink counters is 100. So I've got 4 of those 100s, just like I've got 4 ice creams or 4 lemonades. It doesn't matter. I've got 3 of these 10s and I've got 5 of these 1s, and that's how we write it. We can put it in columns. We can use the place value arrow cards. I'm a big fan of using them together actually with the deans as well, just to augment it. So that's really important, and it helps us with those relationships. Now, relationships between numbers, there are really only 2 key ones, and they are this one on the left. You're probably all familiar with the part whole model, and it really tells us that addition and subtraction are essentially a game. Addition is a game where I'll tell you the 2 parts, in this example 3 and 17, and you have to tell me the whole. Well, I know how to do that. I could that's easy. I could just add 17 and 3 to get 20. Okay. And similarly on the right, you've got the it's not officially called anything because it doesn't seem to have got its way into popular culture. But for me, it's a massively important thing. And I call it the factor product diagram. Works exactly the same way. If I tell you that 6 and 7 are the factors, you can tell me that 42 is the product. We can do this another way. So look, what's changed is now on the left, nothing's changed on the right, but I could have, if I'd hidden any one of those 3 numbers, you could tell me the other. You could tell me what the hidden one was by using the other 2. And similarly on the left, I now know the whole is 17 and one of the parts is 3, so I could work out the other part, but this time I need to use subtraction. I really think that these 2 relationships are at the heart of children's number understanding. And if you combine those with the idea of concrete, pictorial and abstract, then your students will do really, really well following this idea. Here they are, as if by magic in book 1. Here we go. Can you see 3 yellow hats, 3 red hats? and 3 and 3 makes 6. So lots of scaffolding of the language and so on. And there's 5 green balls and 1 orange ball, so 5 and 1. Very clever variation there. Yeah. So I know the whole is 6. Yeah. One more example. All the way up in grade 4. Can you see? Compare the page on the left where we are dividing things. Okay, we've got 69 things divided into 3, and we literally divide our 10s first, and then we divide our 1s, and we've got 23. But then on the right, we do a very similar idea, and yet we're using this kind of much more formal algorithm, but only once that concrete understanding is embedded. So there we are. That was a whistle-stop tour of A, what maths is, B, the subtle changes that we've just focused on thinking and working mathematically, C, some of the Singaporean ideas that have filtered in and fed it and made it a strongish, such a strong program to work with. And I'm looking at the clock. It's 15:46 now. I don't know yet whether our hosts are here, so I'm just going to say thank you, and I'm going to open it up to questions. If anyone has a question, you could pop it into the chat, and I will do my best to answer it. But otherwise, thank you very much for being here. If you don't have questions, there will be certificates sent out, I am assured. And I'm also assured that the recording will also be available. Well, it should be available. Let's find out. I know that's the intention and that's the promise, but technical things can often go wrong. So if you have a question, feel free to put it in. Do you believe the method is applicable past the primary years? Hello, thank you. Do I believe the method? Yes, I do. Actually, I do. Inevitably, there will be less. So actually, when you say method, are you talking about specifically the Singaporean approach? Because yes, they do very, very well at secondary. It becomes more. Oh yes, okay, thank you. Yeah, it does become more formal education in Singapore in secondary. Not to say that it's informal, but it does work. I've seen it, and they do consistently very well. In league tables, particularly international comparisons. Another question here, can I explain the CPA? Yes, sorry. So the idea is that, let me give you an example. Here are 2 things and here are 3 things, okay? And I can count them, and I can go like this, and I can physically work out that I have 5, and that's a concrete thing. But then I could draw them, and I could put 2 with 3, and I could like draw dots, and that's the pictorial. And then finally I could write 2 plus 3 equals 5. Now I shouldn't rush to that 3rd one until I've had a lot of time playing in the other 2. That's effectively it. I could talk for literally half a day on CPA, but that's hopefully the approach. So if a child's not getting something, go back to the concrete stage, then the pictorial, then the abstract. Good question. Any other questions? I've seen 2 questions there. I've got some thank you. That's very nice. Thank you for coming. Thank you for giving me your time. I appreciate how busy people are. Right, there is one more slide, and this is how to get in touch with Macmillan, whom I haven't heard from. So I'm assuming they must be very stressed and very anxious. They were really excited about putting this on for you. So I apologize on their behalf. I know they'll have been sweating so hard behind the scenes to try and resolve their technical issues. But for whatever reason, they haven't. But they have been in contact with me by the chat. So thank you very much, everybody, for coming. And if there are no more questions, which there don't appear to be, then I will. Oh, there's someone else is typing. I'll just wait. Then I will. Maybe I'll just hang around. I'll hang around for another minute or 2 in case anyone else has a question. But otherwise, we'll call it a day. The formal seminar has come to an end, and I hope you enjoyed it. I thank you for your time. And I'm not paid to say this, but I actually think Max Maths is just brilliant. Honestly, it's a very exciting program, and I really hope that if you're not using it, then you will at least go and have a look at it. Okay. Well, here we go. A message from Macmillan. Yep, there we go. They are Oh yeah, it's not what. Yeah, they are here. They're here with us. Just not vocally. They're here with us. Okay, it's not what you know, but how you behave when you don't. Yeah, John Holt, I believe, is the man who said that that quote. A really nice thing about getting stuck. Right. Okay. Formally, I'm going to say that is the end, and thanks for coming.